General relativity, step by step. We've been looking at the linearized Einstein field equations, hoping to find gravitational waves, and we've been applying a sequence of simplifications to the solutions that we've identified to hope to simplify them. And we've already established that k alpha equals 0. That's from the field equations. That's an invariant equation. But now what I'm trying to do is to simplify this A matrix here. And we originally had A mu nu, and now I've got A dash mu nu, which is this equation here. What I want to do is to try and impose some simplifications on the matrix. I'm going to write it down in, it's not a matrix, it's a second order tensor, but we've got t, x, y and z, t, x, y and no, that's x, y and z, x, y and z. And what I'm going to do is I'm going to impose the condition. We know that it's symmetric anyway. No, A dash mu nu is symmetric. A dash mu nu equals A dash nu mu. A restriction which is not altered, or a condition which is not changed by this subsequent gauge transformation in terms of theta. What I'm going to do is require that A dash t nu equals 0. So what I want to do is to specify, that's time, that all these terms here are 0. Simply because it makes it an easier matrix to deal with. That's the first one. This is called the transverse condition. Transverse. And I'm also going to require that A dash mu mu equals 0. Which is telling me that this plus this plus this, I guess plus this as well, but it's 0, equals 0. So the sum of the diagonal elements equals 0. Yeah. Well, let's go with this first. Let's just write down what it is. We want 0 to equal A prime t nu equals, and I'm just going to copy from here, but I'm going to substitute. What we've basically got is that mu equals t time. This is, I'm trying to impose these zeros here in the solution. Equals A mu nu minus. So basically what I'm doing, k is given, k is provided by the physics of the situation, because we know the frequency, and I guess from that we can impute the wavelength. But what I want to do is to find a b which requires, or which forces these terms to be 0 here. So that's k, and I've said that mu equals t, so let's just get rid of that and put that mu there as a t. Now this term here, that's t b nu, nu is free, minus, oh, this interface, oh, here we go. Maybe it'll start to work again. Yeah, minus t, no, it's this term here I want, k nu b t plus eta mu equals t. So that's t nu k pi b pi. K pi b pi. Okay. Okay, so we've got 4 equations here. We've got nu equals t, nu equals x, nu equals y, and nu equals z. And these are all equal to 0. So let's do the nu equals t term first. So 0 equals a, 0, and then nu equals... Oh, I'll write it out. Sometimes I write the time coordinate as 0, and sometimes I write it as t. So it's t, so nu equals t, minus kt bt minus kt bt plus, no summation there, is there? Eta 0, I'm still writing it 0, minus 1, because we've got minus 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, times k pi b pi. And that equals 0. Okay, now nu equals x. Well, I'll tell you what, let me just write down all these equations down, and then I'll show you how we simplify it even more. So we've got t and then nu equals x minus kt bx minus k, it's this term, x bt plus 0, because it's an off-diagonal element of the flat space tensor. Right, now we've just got the same thing, but with x replaced with y, minus kt by minus ky bt plus 0. And the last one, a tz minus kt bz minus kz bt plus again 0, because we've got an off-axis limit. So we've got our 4 equations here. There they are, 4 equations. Yeah, I've already gone, this has gone on too long. What I'm going to do next is to find a sensible k, and we can use that to start simplifying our matrix down. Stop there, stop.